All right, this is lesson 4.1 part 1. Obviously I'm not here today, so you're watching this video instead. So go ahead and follow along with me through these notes, and then you'll have time to work through your homework. All right, 4.1 part 1. Our objectives today are to look at power functions and monomials, and secondly to graph a power function using a table. First and foremost, a power function is any function of the form f of x equals a times x to the power of n, where a and n are non-zero real numbers. For a power function, a is the leading coefficient. And n is the degree. So if we look up here, we have a, that's the number in front of the x, and that's our leading coefficient. X is raised to the power of n. We call that our degree. A power function with positive integer n is called a monomial function. Monomial just means single term, so these power functions are known as monomial functions because they just have a single term, one x value raised to some degree with a coefficient in front. Okay, so we're going to talk about n behavior of different, for a monomial function. So first and foremost, the way we talk about n behavior, the way we look at n behavior for monomial functions is we talk about the degree, whether that's odd or even. And we talk about the leading coefficient, whether that's positive or negative. Okay? So the first one we're going to go over is when the degree is even. And the leading coefficient is positive. Okay, so when the degree is even and the leading coefficient is positive, we're going to get a graph that looks like this. Think about the function y equals x squared. The leading coefficient here would be 1, which is positive, and the degree is 2, which is even. So for an even positive monomial function, our graph will start up, but it will also finish up as we go from left to right. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x is also approaching infinity. All right, so what would the domain be for this function? Well, we can simply look at the example here. The domain, whoops, sorry about that. Domain is going to be all real numbers. Negative infinity to infinity. Or we could write that as x such that x is an element of all real numbers. Either way. Arrows go forever to the left, forever to the right. The range looks like my graph starts here at 0 and goes to infinity. Or another way I could write that, y such that y is greater than or equal to 0. All right, so for an even positive monomial behavior as being up and up. Okay? So as we look from left to right, it's going up and up. All right, number 2. Odd function. And let's look at an odd positive function. All right, odd positive is going to look like this. Example would be like y equals x cubed. All right, positive leading coefficient, which is 1. Odd degree, 3 is an odd number. As x approaches infinity, f of x also approaches infinity. As x approaches negative infinity, we see that f of x approaches negative infinity. So what's this graph doing? It's down and up as we look from left to right. The domain of this function is still all real numbers. And the range is also all real numbers. If you see, it goes forever down and forever up. So the range is also all real numbers. That would be y, such that y is an element of all real numbers. Okay? So that's what we have for our first 2. So we've got even positive and odd positive. We're also going to have even negative and odd negative on the next page. So let's do that. All right, even negative. Well, you remember what a negative a value does to our quadratic functions. It makes it open down. So our graph is going to look something like this. An example of this graph would be y equals negative x squared, where the leading coefficient is negative. The end behavior then is as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x also approaches negative infinity. Domain is all real numbers, as you could imagine. Forever left, forever right. And the range this time goes from 0 down, or goes from negative infinity to 0, is how we write that in interval notation. I'll skip set builder for the sake of time. All right, there's your even negative. Let's look at odd negative. All right, so odd negative is going to look like this. Example would be y equals negative x cubed. So as x approaches infinity, as x gets bigger, y gets smaller, so f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. Domain is still all real numbers. Range is also all real numbers. All right. Oh, so we forgot to label this one. We would call this one down and down. And this one would be up and down. And we're just saying the direction of those arrows from left to right. Up arrow to the right, down arrow, up and down. Okay? Cool. Well, let's look at the next example here. Our first example, I should say. Describe the end behavior of f of x equals negative 2x cubed using the leading coefficient and the degree, and state the domain and range. All right, well, the leading coefficient here, is it positive or negative? Well, let's look at the number in front of the x. It's negative. And the degree is 3, which is 3 an odd or an even number? It's an odd number. So we are dealing with a graph or a monomial function that is odd and negative, odd, negative. Well, that's up here, odd, negative. So it's going to have all these characteristics. It's going to have this end behavior. So as x approaches infinity, f of x approaches negative infinity. as x approaches negative infinity, f of x approaches positive infinity. Domain, negative infinity to infinity. Range, negative infinity to infinity. Right? So now if we wanted to graph this, we could do a quick little sketch, right, of just what the end behavior looks like. Or we could pick a couple values. Let's do a couple values real quick. X, Y. Okay. If I plug a 0 in, 0 cubed is 0, right? So negative 2 times 0 cubed equals negative 2 times 0, which is just 0. Okay, so it's going to go through 0, 0. Let's do a negative 1 and a positive 1. 2 times negative 1 cubed. Ooh, so here, negative 1 cubed is negative 1 times negative 1 times negative 1. Because it's 3 times, it's going to stay negative. So this is negative 2. So when I plug a negative 1 in, I got a negative 2 out. Oops. No, I get a positive 2 out. I forgot about this negative in front. So it's actually a positive 2. Positive 2. So negative 1, positive 2 is here. And then we know if we plug a 1 in, that's just going to be negative 2. Whoops, can't see that. That's just going to be negative 2 times 1 times 1 times 1 is 1. So that's negative 2. So 1, negative 2. So you can see it's going to kind of go curvy through here. It's a little steeper than our other graph, but same exact end behavior as this one up here, right? Hopefully you see that. Flip it over. All right, at this point you can pause the video if you want to try this one on your own. After you unpause, I'll do the work and show you the answer. If you want to do it, pause now. All right, we're back. Here we go. Let's see. Describe the end behavior, domain, and range. End behavior is as x approaches infinity, f of x approaches something. As x approaches negative infinity, what's f of x doing? Right. So let's see if we can figure this out. Well, it's negative, right? And it's even. Even negative. If I remember from the other page, even negative looks like this. Down and down. Okay, so as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, so does f of x. Cool. Domain for this over here is going to be all real numbers. Range for this over here is going to be negative infinity to 0, including 0. Hopefully you got that correct with all the information that you gathered up on the first page. All right, example 2. For water to flow through a garden hose at a certain rate in gallons per minute, it needs to have a specific pressure in pounds per square inch. Through testing and measurement, a company that produces garden hoses determines that the pressure P given the flow rate F is defined by P of F equals 3/2 times F squared. Graph the function P of F and state the domain and range. All right, so first find A and N. So for the leading coefficient is 3/2, which by the way is positive. And N is 2, which by the way is even. Okay, even positive. If I'm just thinking about that, up and up. Up and up. All right, so find the domain. We don't even have to graph it yet. We can find the domain just using this. The domain is negative infinity to infinity. Because A is positive and N is even, the range is 0 to infinity. All right, create a table of values and graph the order of pairs. All right, So you can just plug this straight into your calculator if you want, but I've given you some values in this table. So you can either pause the video now and fill this in and graph it, or you can follow along with me. If you want to do it on your own, pause the video now. Otherwise, follow along with me. All right, so I'm just going to do this on my calculator. If I want to do 3 over 2 times negative 2 squared, I would just put it in like that. Turns out to be 6. Do 0 next. 3 over 2 times 0 squared. 0, no surprise there. We already got 1.5 given to us, that's great. Let's do the next one. 3 over 2 times 1 squared, 1.5, and 6. Hey, look, there's symmetry here. That's cool. So let's graph it. 0, 0, 1, 1.5, negative 1, 1.5 is kind of right there. Negative 2, 6, and 2, 6. So we get a graph that looks just like this. Okay, which is very similar to what I sketched earlier, up and up end behavior. And so we're all good with the information we provided here. All right, well that wraps up lesson 4.1 part 1. Feel free to watch back any parts of this video that you need or slow it down to fill in your notes. But at this time you can go ahead and do your homework. Thanks for following along. See ya and have a great long weekend.